please go ahead and say hello, introduce yourself, share, what school or what you're studying, what country you're participating from. We've got 3 presenters today, and the first is going to be Dr. Lee. And Dr. Lee obtained his Ph.D. in August of 2021, so congratulations, that's not so long ago, from the University of Utah. So he previously worked on smart stormwater systems and urban flooding resilience, so an area I'm personally very interested in, and now is working as a full stack software developer at the OWSI lab in Colorado State University. And in this role, his work includes, but it's not limited to, big data, scrapping cloud service-based web tools, and deep learning models. So very interesting stuff. So Dr. Lee, you should have co-host abilities, so you can share your screen, and we're very excited to hear your talk.
Thank you, Jennifer. Can everybody see my screen right now? Because
it's loading.
Okay, sounds good.
Yeah,
that works.
You just need to switch to presenter mode.
Yep. Okay. Because on my side, looks
straight now.
Looks great. Okay.
Yeah.
Cool. Thank you, and thank you, Jennifer, and hello everyone. My name is Jiada Lee, and thank you for joining my talk. I feel so excited to share my research in this early morning. And I'm going to cover my dissertation research, which is about using smart stormwater real-time control to enhance urban flooding resilience against rainfall and land cover changes. So to make sure we are on the same page, I'd like to go first to introduce some research background. And this research map, which is a flooding risk map, was generated by the First Street Foundation, which this one shows the changes of the estimated economic loss due to flooding from 2021 to 2051. And as you can see that in the Western US, there are many more blue blocks around the Western states, indicates that the urban flooding are projected to increase significantly. So when we look at the Utah, and it shows there is an about 11% increase in the average expected annual loss due to the land cover change and the climate changes. So as the cause of the urban flooding on the climate side, and I observed a slight increase in the precipitation depth from 1980 to 2090. So these results are based on the global climate models. Although there are some uncertainties and land stationarities in the precipitation and data, and the increased trend for all climate scenarios, including the RCP 2.6, 4.0, 4.5, 6.0, and 8.5, all of these climate scenarios shows a slight increase about the precipitation volume. In the urban land cover side, and for instance, I take an example of the sugar house area in the Salt Lake City, Utah. As the population increase and the cities need to rebuild and redevelop the urban areas to make the residential units to be higher and taller, which requires much more impervious areas for the land resource and the surface areas. So these changes in the land cover type and also the precipitation has caused more frequent urban flooding events in the local area and the residential communities. This flooding issue motivates me to doing some research to better understand the flooding dynamics, and also seek to control the flooding dynamics in the local areas. So as I say it, and the system capacity cannot stand the stresses from the extreme weather changes and also the rapid urbanizations, and there will be more and more flooding events. And so far, there are 3 popular mitigation strategies are used to alleviate the flooding situation. The first one is to recite the green stormwater infrastructures. But this option 1 has to need much more money and around the resource to achieve this kind of practice. The second option is to install the green stormwater infrastructures, which is abbreviated as GSI. And this option is very popular to absorb and infiltrate the stormwater runoff, because this is a more cost effective than the option 1 by mimic the natural plants and also some land structure practice like the rain gardens and green roofs. The third option is to real-time sensing and controlling technology to dynamically and adaptively to remove the extra stormwater volume and the peaks. But this technology is still in the early stage, so there is models for simulation and prediction the performance. And this option 3 also needs field instruments to collect the data for the real-time control operation. So in terms of what I'm introduced above, and the research gaps come from 2 points. The first point is the comparison between the real-time control and green stormwater infrastructures, from which flooding mitigation is seldom conducted. And the second gap is from the system failures. These are resilient adaptive measure to climate change, but only green stormwater infrastructures are discussed in the previous adaptation studies. So, based on the research gaps, and I proposed my research question, which is can real-time control outperforms green stormwater infrastructure in enhancing the future flooding resilience under the changing climate and urban land cover changes. With that, and I looked at the Sugar House area in the Salt Lake City, Utah. So why I choose this study area? So basically, there are a couple of reasons, but some of the important reasons, like this is our very high population and density areas, and with a very outdated stormwater infrastructures with ages from 10 or 30 years. And also this area has very lower elevations. If this rainfall comes and the runoff will automatically accumulated in the study area, which makes this area as ponding areas. And so, and also there are some very extreme storm events in 2017 and 2021 summer. To do that, and I simulated the existing green stormwater infrastructures using the SWMM model. And so this model was used to capture the 80 percentile rainfall event, and the 3 bioretention cells and 2 permeable pavement are distributed along the subcatchment. For instance, like the subcatchment ID showing in the red faults, SC 15, 16, and 18, and SC 4 and 1, this catchment. For each subcatchment, and 50% of the impervious area are designed as a bioretention and 10% as a pavement, which is about 100 to 400 square feet. In terms of the real-time control, and so 3 control sites with storage pond are selected to implement the real-time control. And so, for instance, like in the Sugar House area cartoon, there are 3 storage pond, and the control site are skeletonization as the SWMM model to operate the real-time control gate opening and closing, as is shown in the SWMM models from tank 1 to tank 3 in the distribution of the locations. And also, I want to also show you some the conceptual design of the real-time control in my study areas. So basically, in the real world, the real-time control use sensors, and for instance, like the flow sensors and water level sensors, and also some rain gauges to collect the real-time data. The real-time data will be used as the input for the actuators, for instance, like the gates and the wheels, to achieve the continuous monitoring and the dynamic controlling for the system, as shown in the blue side, which is dynamic cartoons. So sensors provide real-time informations like the real-time informations and the system states to the operations of the gate, and then the actuators will adjust the gate opening, maybe for instance, like by 10% or 20% or 30% based on the water levels in the storage tank, or the flow and outflow from the storage tank entering into the pipeline system, so they can control the water level of the plant, and also achieve the potential interventions in the system to be more dynamic to the different situations. With that, and so basically the implementation of the green stormwater infrastructure and real-time control will change the system drainage system's performance. And I used the system performance, which was introduced by the Berger, which they published this system performance curve in 2015. And this system performance curves include the rebundantness and the resistance failure stage and the recovery stage. So if there's a rainfall comes, the system performance curve will drop down and then reach the maximum failure stage. If the rainfall decreased, the system will recover back to the original state. So as you can see that if we implement the green stormwater infrastructures or real-time control into the drainage systems, the system performance curve will be promoted from different stage. I basically used the equations in the bottom to calculate the flooding resilience, and the flooding resilience will be calculated with the integration of the area of the shaded area, and then use 1 minus to the shaded area to get the flooding resilience value based on the equations as shown in the bottom. So moving to the results section, and I compared the system performance curve and 3 scenarios. For instance, like the blue curve, the blue curve is the baseline scenario, and the red curve and the black curve is the real-time control scenario, and also the green stormwater system scenarios respectively. So in figure A, the real-time control has consistently outperforms the GSI during the long-term continuous simulations. But both RTC and the GSI has a higher performance than the baseline scenarios, which means RTC and GSI are effective solutions for the flooding mitigation. And when we look at the individual storm events, which extracted from the continuous simulations, and for the resistance stage, the system performance curve in the green stormwater infrastructure has a quite slower falling depth of the, which means falling stage of the performance curve to improve the system reliability, resistability than the real-time control. But when we move to the recovery stage, and with recovery stage, and the RTC, the real-time control has a lower, which is the red curve has lower levels and a faster recovery rate than the green stormwater infrastructure. So this finding is quite interesting information, which means the green stormwater infrastructure can resist the disturbance, like the rainfall changes or the cover changes better than the return control. But after the system failure, if the system wanted to recover back to the original state, the return control would be better than the green stormwater infrastructure to help the system recover back to the original state. So I also looked at the individual dry storm events, and under the 2-year, 10-year, and 100-year 3-hour storm event, and the duration of the 100% gate opening is extended by about 20 minutes from 2-year to 100 events. This operation helps the storage tank to release outflow to the downstream side and to prepare much more available storage space for the incoming storm events. And so this kind of operation of the return control for the individual events has helped the system to prepare sufficient storage value when there is rainfall peaks or extreme rainfall values comes in the next storm event. So to wrap up, and I'd like to give you 3 key takeaways. And the first is that both the green stormwater infrastructure and the return control are effective adaptation strategies by improving the resilience up to 30% and 70% respectively. Yes, this is really meet my expectations. And the second is the return control can perform better than the GSI as a crucial component of long-term resilient stormwater management. Because what I want to do is, for my research, is want to investigate the long-term stormwater resilient management, but not the short-term. So the return control perhaps performs better than the GSI. And the third one is return control to keep consistent performance in the back-to-back storm events, as I mentioned in the continuous simulations, and the return control leaves a trade-off between the dynamic control operation and the system functionality loss. So this is very important when we want to implement this re-emerging technology in our stormwater system to help us mitigate the flooding. We need to be careful about the control operation and the system functionality loss. So that's all. Thank you for listening.
Thank you.
Okay.
So that was very interesting. I'll invite, are there any questions from the audience?
Mm-hmm.
You can either raise their hand or type them into the chat. It's Professor, right? Professor Zhao? Go ahead.
Hey, Jiada, thank you for your presentation. Very interesting study. I'm just curious, can you, maybe I missed that, can you share with us a little bit more about where your control facility is and what are the control rules you are implementing?
Yeah, and so I think let me get back to share the screen. Yes, the control rule is kind of like the rule, I did not introduce much more about the control rule, but I'd like to introduce so the control rule is based on a rule-based control. Basically, we implement if and then rule into the SWMM operations using the Python wrapper. And so, but I forgot to add the backup slides over here. So the rule is based on if and then rule. For instance, like if the rainfall and also the water level is over a threshold. For instance, like the water level is over 0.5 meters, and we will send this information to the return operations to open the gate or close the gate by 10% or 30%. So that's the basic rule. I know there are lots of studies are using some very advanced control rules like reinforced learning and also some water predictive controls, but that is very quite complicated, especially sometimes they will show some disadvantages to the small study area. Because my study area is quite small, so that's the reason I only choose the rule-based control, which is if and then to operate the gate and orifice openly.
Okay.
Yeah.
Can I ask a follow-up? Like,
sure.
So based on your experience, like how different those control rules can play a role here? I mean, are they, if you implement a different rule, like do you expect a significant difference or not much difference?
Yeah, that's a good question. And so I think that is very quite. I tried a lot of implementations of different control algorithms, and that really depends on your system input. For instance, like the what's the baseline of the water level, and how much, for instance, like how much flooding, how much rainfall intensity, and in your study area. If you're rainfall for some very humid study areas, and if you use very complicated stormwater control algorithms like water predictive control or the reinforced learning controls, the difference were quite big. But if the system input, like the rainfall intensity or the runoff changes is quite is not so big. For instance, like in my study area, it's very dry areas, and the rainfall changes is not so big, and the difference of the performance will be not so significant. Yeah, so that's what my thoughts. Yeah.
Okay, thank you so much.
Yep.
Thea, do you have some questions?
Yes, I do have. It's great presentation. I just want to ask something. Like, you have run some design storms. Have you find any flooding in the upstream when the gate was closed during your any of rule? When you are running like 100-year flood, which is very high rainfall?
Yeah.
Small catchment.
Yeah, right. Yes, correct. And so this is so firstly, that's the reason the system return control need the return control need a system view. And so what is the system view? And as I said, in my cases, when I'm running my simulations of return controls, for instance, like if I want to control for instance, if the downstream have a flooding point, and what I want to do is to close the gate in the upstream pond. But if I close the gate for a long time, like for 24 hours or 60 hours, the pond in the upstream will cause overflow. So we need to balance the upstream and the downstream flooding situations. So that's the reason we needed to a system view when we needed to implement the return controls. And as also I mentioned, like in my third takeaway messages, and we need to be careful about the functionality loss and also the dynamic controls. Yes, I think most of researchers, they maybe want to implement the return controls as extensive as they can, but sometimes they will reduce the system functionalities. For instance, if the upstream, if they close the gate for a long time, the overflow will occur in the upstreams. So the system functionality, the whole system functionality will lose. So that's the reason. Yeah, as I mentioned, we did a system view to coordinate the overall control in the system. Yeah.
Thank you. I just have one more follow-up question. So this looks like very high urban catchment, and there should be very like flash flooding. So do you have any idea how long it take gate to open and close in the real-time system?
Yeah, and I think I tried in my studies, and I tried so for instance, like for instance, the timing of the open the timing of the open and close the gate it depends. My suggestion depends on the peak flooding, how long your flooding peak will last. Because what we want for my study area, I want to shift. I want to shift the flooding peaks, because the flooding peaks is sometimes the most serious issues in my study areas. And for my study, and the flooding peaks are extended by 20 minutes and from 10 years to 100 years. So for this kind of study cases, and I suggest to the timing of the opening of the gate should be matched the peak flooding durations, like 20 minutes. But if you have a study case which has flooding peaks about 30 minutes or 1 hour, that would be better to extend your gate opening to 1 hour or maybe 1 hour and a half to cover the whole peak flooding timing. Yes.
Okay, great. Thank you.
Yeah, no problem.
Are there any other questions from the audience? So I've got one.
Sure, no
so I'm really interested in smart stormwater systems, and I see the potential for it. But one of the practical obstacles that I always get kind of hung up on is how do we deal with, or how do we plan for like unintended consequences? And a local example for me, there was one of the cities in my area had a stormwater or overflow tank that had a gate that was left open. And it was left open. So the opening was small enough that the sensor didn't, like, it was within the sensor, accuracy range. So it wasn't picked up. And so the overflow gate, which contains, like stormwater plus sewage, because it's a combined sewer, leaked for 4 years. And when it was finally discovered, it was something like 24 billion liters of water had been like discharged unintentionally into, like a wetland or a receiving water system. So, since, as someone who's worked in this area, how do we design these systems to fail in a way that's going to be, in a way that we can anticipate the unexpected? I'm very curious to hear what your thoughts are. How do you stop these really like unintended accidents?
Yeah, I think this problem is quite as common, around the world, like the unintentional discharge of the discharge to the sewer systems. So you might thoughts, because like the return control for my side, I'm doing like to mitigate the stormwater system. But if we want to mitigate the overflows, which is caused by the intention, like the combined sewer overflows from the unintentional discharge, and the best way is to identify the hot spots of the firstly to identify the hot spots of the combined sewer overflows, and then implement the distributed rate control in the study areas. And because we cannot implement the rate control everywhere, firstly, they will cause lots of costs, and it's quite expensive. Secondly, the performance of the control will decreased as the control site increased. So basically, the performance of the distributed control will be like a logistic curve. They will increase first and then drop down at the, or maybe reach the maximum performance at the increase of the number of the control site. So my straightforward suggestion is to identify the hot spots of the capacity overflows, and then to investigate if we can implement the rate control in this study area, in this hotspot area, and but the installation and the implementation of rate control in the field work really depends on the location's space, and also some other scenarios. So, but the first Yeah, but the first step is to identify the compressive overflow hotspots, and then to investigate the return control in the hotspots. That's the suggestion. Yeah.
Just a follow-up question. In your project study site, did you explore in your simulations sort of failures? Because green infrastructure is just as susceptible to failures as well. Like they get clogged and then they don't provide the detention, or did you do any scenarios of like, oh, the gate didn't open, to look at the risks that these infrastructure actually generate or create? Because as soon as we bring in a new technology, there's always going to be a failure risk associated with it.
Right. Yeah, I definitely. And so in the simulations, the failure of the return control can be defined as the gate opening is over 100%. So yeah, because in my control algorithms, and it's based on it's a linear relationship between the water level, between the system level, between the water level and the opening percentage of the opening gate. For instance, like if the rainfall intensity is or the water level is very higher, and the means my gate should be open very high. Sometimes it will reach or over 100%. But in reality, I mean, in the real situations, we cannot open the gate over 100%. So that's if the mathematical stuff, if the mathematical operation, if the mathematical algorithm output the opening gate over 100%, for instance, like 120%, that means the failure of the gate. So we consider this kind of situations as the failure of the system, yeah, of the return control system, yeah.
All right. Well, thanks you. That was very interesting presentation and discussion. Thank you so much. We'll do one last question before we move on to the next speaker. I just saw this in the chat. Hassan, I hope I pronounced your name properly, was just wondering how about to place GSI followed by real-time control? That's an interesting idea, using these two things in conjunction. Is that something you've looked at all?
I haven't looked at these options, but I know some there are some literature reviews and has implemented the return control in the green stormwater infrastructures like bioretentions or some other practices in practice. But I think that would be sure the addition of RTC to the GSI would be I mean, just for the performance as perspective, the addition of RTC to GSI would be better than individual RTC and GSI, but we need to think about the costs or the maintenance in the long-term continuous monitoring. So on my start error, and because I'm doing long-term management, long-term resilient stormwater management, so I did not consider the addition of GSI and RTC. And so for my plan, and if I want to evaluate these scenarios, I'd like to do the evaluation maybe just based on the short-term simulations, or like for instance, like 2 days or 3 hours or 12 hours for the evaluation. Yeah.
Okay. Thanks. All right, so we're going to go now to our next speaker. So Zia, that's going to be you, because we're one speaker short. So Zia Hassan did his bachelor's in agricultural engineering at the University of Agriculture in Pakistan, and a master's in water engineering and management at the Asian Institute of Technology in Bangkok, Thailand. After doing his master's, he worked for a couple of years as a water resource engineer, and is currently now in the 3rd year of his Ph.D. at Kent State University, Ohio. And his research interests are climate change, urban hydrology, and numerical modeling of water resources. So you should be able to share your screen. You should have co-host abilities. Welcome, and I'm looking forward to your talk.
Okay. Can you see my screen now? Not yet. Can you hear me?
Yeah, we can hear you. We can see your screen. You just got to switch to presenter mode and you're all good.
Okay. So thank you again for the introduction. So today I am going to present about climate change impacts on urban stream flow, implications for the stormwater management. So mostly this talk will be focused on how the climate change is changing into the future, into the urban catchment of Ohio. So here is a little bit introduction. So why regional climate is important? It's because low flows and high flows in the streams. If there are high flows in the 35 years of interval, historical, initial, mid, and late century. So I just want to compare historical with all three periods, like how climate is changing into the future. So also we have done disaggregation of the precipitation data because we got hourly data from the RCM, but we calibrate our model for every 5 minutes of data. So I disaggregate precipitation from hourly. I'm going to present, I will present temperature, how it's going to change into the future, precipitation and depth duration frequency curves, flow duration curves, and some flood frequency analysis, which I have done by using Gumbel distribution. And then I have run some stormwater scenarios, and I will explain in my slides next. So here you can see the historical and future temperature. So how it's going to be changed. On the x-axis, there are months, and on the y-axis, it's the mean monthly temperature. You can see here the box plots. All box plots represents 4 historical, initial, mid, and late century. The black line in the middle of this box plot represents the median of this temperature, how medians are changing into the future. And you can see that all 4 RCMs are showing us that there will be an increase in temperature in all periods. Even during the summer months, when the temperature is like our mean temperature is around 20 to 25, it's going to change up to 30 degrees. So what I found that if I can say that there is a single value of yearly, so I can say that it's going to change around 5 to 6 degrees Celsius into the future. So same here. So I have used 4 different RCMs. I have removed the outliers for the extreme events from this graph. Similarly, in this graph, you can see this is the interquartile range and also in the median of the precipitation. What I have found that summer months, when there is more precipitation already in the catchment, it's going to be more wet. Like wet months are getting more and more wet. And during the winter, when there was not a lot of precipitation, so it's also going to increase into the future. So here is the depth duration frequency curves, and WQV represents the water quality volume. Basically, water quality volume is the amount of rain that should be captured and treated by storm infrastructure to remove the majority of the stormwater pollutants on an average annual basis. So basically for the Cleveland region, water quality volume is approximately equal to 1 year and 1 hour storm. So this is the water quality volume that is used here in the region for the design, in the Cleveland region for the design of the stormwater infrastructure. So here you can see on the graphs on the right hand, I have used 4 different RCMs, and this dashed line here represents the water quality volume. We can see that water quality volume is increasing into the future for all the return periods. I have 6 months, 1 year, 2 year, 5 year. So 1 year, 1 hour storm that is used mostly for the design of storm infrastructure is going to increase up to 35% into the future. And all 4 RCMs are almost showing me the consistent results. So it means that rainfall depth of water quality volume will be most frequently exceeded for the historical 1 year. So this line represents the historical, and this is 1 year flow, and you can see that it's going to increase into the future. And also for the late century, 6 months, recurrence interval, and it's going to increase into the future. So here is another depth duration frequency analysis for 2 to 10 year return periods. So 2-year and 1-hour storm are important in this region for the design of roadside ditches. So it's we can see that it's going to increase by 14 to 33% into the future based on all 4 RCMs. And there is RCM to RCM variability. That's why I am showing here range like 14 to 33%. So here is 5-year 1-hour storm. That storm is used for the design of storm sewers, and 10-year 1-hour storm is also in some urban areas is used in the state of Ohio for the design of storm sewer. So both of them are going to increase up to like 33% and 22% into the future. So what does mean? It means that we need more or bigger stormwater controls to overhaul the existing infrastructure. So once I looked into the precipitation patterns, so here it comes that I explained in the calibration part, I took the 224 parameters to get the uncertainty associated with the calibration parameters. So here is the 224 on the x-axis, there is the accidents probability. Higher the accidents probability, the lower will be the flow into the stream. So lower the accidents probability, it means the high flows into this urban stream. So this is the 224 parameter sets, and the black line in the middle mention represents the median. So like how flow duration curves is going to change into the future, I have presented here 4 different RCMs and 4 different periods. So as compared to the historical, which represents here with the blue line. So these lines, 4 lines represents the median of these 224 parameter sets. So we can see in the blue line that all the future periods are going to increase into the future. And also you can notice one more thing, that in future the difference between historical and future periods are higher as compared to the difference in between initial, mid and late century. So based on this accidents probability and flow curve or flow duration curve, high, moderate and low flows are going to increase into the future. Some RCMs showing that extremely low flows are not going to increase that much, but some are showing that it's going to increase. There are some modeling limitations of low flow into the swim, so I will not focus more onto the low flow end of this curve. So once I have these, then I have done the calculations by fitting the Gumbel distribution, and I have calculated the flood frequencies, like how flood frequencies are going to change into the future. So here is the 2-year return period of the flood. So each black dot here represents each of the parameter set that I use for the calibration, and each of the graph, different color represents different RCMs. So here on the x-axis, there is a period like initial, mid and late century. And on the y-axis, now I am mentioning here the percentage change as compared to historical. So we can see that 2-year and this is the like graphs represents the distribution of those 2-year flood frequencies. So we can see that it's going to change almost in the initial century by 70%, and up to the late century, the 2-year flood frequency will increase by more than 100%. Similarly, I have found for the 5-year return period. So here is the percentage change. You can see that only one RCM showing that it might decrease into the future, but all other 3 RCMs for initial period, but all other 3 RCMs. So main purpose of using 4 different RCMs is to capture this variability, like how RCM to RCM projections are going to change. So you can see here, like it's going to be almost 5-year return period flood will increase by 100% in future. So here is little bit high frequencies of flood, like 10-year and 25-year. So we can still see that it's almost going to increase more than 100%, like 10-year and 25% flood into the future. And almost all RCMs are showing us that they are going to increase into the future. So now this is the climate change part. Now I just run some of the low impact development simulation like stormwater management scenarios. So for that, I have used SWMM algorithm, and I have run 30,000 different simulations for the optimization of the green infrastructure. For now, I am just adding the permeable pavement into the catchment. So what I got, like if I increase the imperviousness into the, if I reduce the imperviousness into the catchment by 14%, I am going to, like in the SWMM, I have objective function to reduce the flow volume. Flow volume is like the volume of the whole year of flow, and the peak flow is the flow volume of the highest flow event into the catchment, into the hydrograph. So we can see that peak flow is going to decrease by 5% and by 14%, and flow volume is going to decrease by almost 5%. So what I increase then linearly, like 14, 27, 41, and 55%. So what I got response that if like response of flow volume to mitigating impervious areas by green infrastructure is non-linear. Because if I see that 14% is going to decrease the flow and flow by our flow peak flow by 13%, but if we add additional 30% more infrastructure, so it's going to increase by only 15%. So now this is the research question on which I am currently working. How much additional green infrastructure is required to offset climate change impact? Because we see that 2-year floods are going to increase by almost 100%. But with almost reduction in the 55% imperviousness, we have only decrease in 15% of the peak flows. So here comes the future work, which I am planning to, which I am working in my PhD. So in the future, this is only permeable pavements as a single LID. So what I am going to do, I am going to get the regional mixture data for the Cleveland and going to run the scenarios based on what is the existing green infrastructure into the catchment. So those will be the more realistic scenarios. And also in this project, we have collected some. So Kelly Turner, who is collaborating in this project from University of California, so she have collected some storm surveys from the Cleveland region. So we have data from storm surveys from different stakeholders that how they are going to implement more infrastructure in next 5 to 10 years. I am going to put that scenarios in this calibrated model and run that, see how we get the difference or we are able to mitigate the impacts of climate change. Also, I am planning to extract some data from policy documents from state of Ohio or county level policy documents. And also at the end, I am going to talk with the expert opinions in the region of the Cleveland. For example, Northeast Ohio Regional Sewer District, who are working directly with the stormwater control, that how they are going to implement the scenarios. Then I will model those scenarios and see that what we will get the impact on peak flow and also the total flow volume. So what is my conclusion and implications? Like Cleveland precipitation amount and increase in intensity will increase over 21st century. So existing conveyance infrastructure will be more frequently overwhelmed because we have seen that whole return periods are exceeding from the water quality volume into the future. So what will happen? The existing green infrastructure performance is going to decrease because we have not considering here the climate change when we are designing the green infrastructure. So 2, 5, 10, 25, 50 and 100 year, I have done 50 and 100 return year big floods also analysis, but I have not included that in this presentation. It's going to increase into the future due to climate change. And also based on the flow duration curves, we can see that stream high flows will increase without increase in stormwater management. Stormwater planning should take climate change into the account when we are designing different green infrastructure. So at the end, I would like to acknowledge Northeast Ohio and my advisor, Dr. Jefferson, and also all the collaborative in this project, and also Ohio Supercomputer, who have provided opportunity to run the 100 years of simulation online like that big model. And also at the end, I am thankful for NSF for providing the funding for this project. So thank you. So if you have any questions, please let me know.
Thank you, Zia. That's some really interesting climate data that you're producing. I'm sure there's lots of policymakers in Ohio that are interested in some of those results. Are there any questions from the audience?
I got one.
Yeah, go ahead.
Hi, Hassan, and so a very interesting talk. So from my understanding, like I know there's a trend that the public utilities, they wanted to update the IDF curves by considering the climate changes, and but sometimes as you showing for us, and the intensity and the rainfall depths are increasing in the future, and but this is for the system as for the IDF curve design side, and but for the infrastructure side, and when the engineers going to design the drainage infrastructures, they may be over designed or under designed the system in the real world. So for this kind of cases, for instance, if the drainage system are over designed, and also how to use your generated IDF curve to guide the engineers to rebuild the system. I mean, what's your suggestion? Like, how do they use your research for the under-designed or over-designed system? Yeah.
Yes, thank you. It's a good question. So this under design or over design basically mostly depend upon the uncertainties associated with the projections which I am doing. So I have just tried my best to project based on 4 RCMs and based on very high resolution of data, like every 5 minutes of rainfall data. So that's why whatever I am like I am suggesting, so I am using a range of the values that this could be the possible by using multiple RCM. Of course, they don't want to design for the over because it's not the cost effective. So what I would suggest, like they should be like come up with a decision, maybe the median of some values, and also if they are going to be designed for different green infrastructure into the future, I am going to use some cost-based optimization where they can design the green infrastructure, but based on the cost. So I will use this ostrich swim algorithm so that they can design the efficient infrastructure with the minimum cost. So they can identify the locations into the catchment where based on this like algorithm, like they can like have many possibilities where they want to invest into the green infrastructure. So based on that, so they can I can suggest the solutions that have minimum cost and maximum benefit. So that's why I am planning. And also I am trying to capture some uncertainties. You can see here, like it's going like each of these parameters associated uncertainties, which are like more like I can identify it by using numerical models. So I am giving a range. So hope so like this will help to understand your answer.
Yes, thank you.
Yeah.
Well, Zia, I have a question. I think your results, is particularly about the water quality volume, are really important and interesting. And I'm just curious, are you planning to look at then the implications to pollution? Because if your green infrastructure, right, it's gonna be overwhelmed more frequently, and so the water quality volume is too small, which means there's actually the pollutants that are going to be released are going to be higher than we're anticipating too, right?
Yes. So basically, I have discussed this thing in the very beginning of my PhD, that can I include the water quality with my advisor? So basically, the problem here is the data for the calibration. We do not have enough data available for the calibration or water quality samples, so that I can calibrate my model so that we can do some real predictions about the water quality too in the catchment. So, but if I want to include, it's a lot of work, and I only have like maybe 1.5 years left for my PhD. But this is very interesting work if somebody want to continue after me.
Yeah, I think it's certainly something to have in your last chapter of your thesis, is like the next logical question, because given just for your region too, I'm sure TMDLs is such a big thing that this is something that I'm sure a lot of policymakers are going to be concerned about, because there's the pollution estimates and the amount of release of phosphorus and everything is going to be wrong.
Yes. So maybe I can look in the policy documents and see like something I can suggest based on the existing literature in my like discussion section of dissertation, but I am not planning to include that in the modeling stuff. So there's a lot of work.
What like for the policymakers, with what you've done so far, what is your recommendation of what they should do to get ready for the changing climate that's going to happen?
My first suggestion is I have presented this work once in the Ohio Stormwater Conference, and there are some people who are interested in this work based on the water quality volume that I am projecting that it's going to be increased into the future. So actually I am going to write, once I will finish writing paper, I am going to write a technical report for them if they want to include these results into their future planning of the green infrastructure. At least update the water quality volume, which is important for the design of green infrastructure in the region, because like lot of like world is moving towards green infrastructure. So at least they should like improve the water quality volume for the future, not only based on the historical rainfall. They should at least consider for the new infrastructure, the water quality, updated water quality volume. So hope so I will write a technical report for them with the collaboration with my advisor in future.
Yeah, very, very interesting work. Are there any other questions from audience members?